Hello, today we're going to talk about discrete control and programmable logic control, or PLC. Alright, so the mainly two topics. The first, let's look at discrete control. So discrete control means the value of the variables are discrete numbers instead of continuous. There are a lot of discrete parameters. For example, if the sensor is on and off, or switch, or timer. So timer only takes discrete values. For example, 1, 2, 3, 4, 5, right? A switch, a limit switch, will take it on and off. So those kind of switches or sensors, or actuators. So they only take the discrete discrete numbers. Those are called discrete control. Those discrete controls can be normally used in a lot of those discrete event production. For example, you have separate parts, then make one by one. It also can be used in a lot of continuous processes, right? So, for example, when we are making processing gasoline or any kind of liquid or biomedical processes, that is related to liquid or fluid, there are also a lot of switches and also sensors that can sense on and off, or inflow and outflow. So those are also discrete controls. So which means that discrete control also used in continuous processes. Two categories of discrete control. One is the logic control, the other one is the sequencing. So the logic control means the value of the control device is driven by the event, and sequencing means it is related to the time event or time driven. For example, what is a logic control? Say you like spaghetti. All right. So if your parents provide or prepare spaghetti tonight, and for the dinner, you will eat it. If they are not preparing spaghetti at night, you will not eat it. So in this case, are you gonna have dinner or not? Right. So this action is dependent on what? It's dependent on, do they prepare spaghetti or not? Right. If they have this spaghetti, then you will have dinner. Otherwise, you are not gonna have dinner. So this is event driven. It's not related to any other kind of things. It's only related to that event. While sequencing is, for example, you have a timer, and when a switch is turned on, or the timer is turned on, it will start to count, like 1, 2, 3, 4, 5, and then it will do what, right? So use that to control the other devices. So both of those categories are referred to as switching systems. So they can make some switches, right? Because they can show their outputs values either on and off. And so some of the features about logic control is that it can be determined exclusively by the value of the inputs. And so, for example, at any moment when the event happens, then the output will happen, right? So it does not have a scheduled or something, right? Another thing is no memory. So it's not we do not need memory to handling any kind of data. Because all the switches are based on electrical current, and also it's not dependent on the time, right? It's dependent on the event. So logic control. So there are some of the basic elements about logic control. When I talk about this, you can tell the device or the system is actually controlled by the logic. So what are these logics? Typically, we have logic of AND, OR, and NOT, right? So the AND means, when both input values have positive value or 1, then all the inputs, then the output will be 1, right? Well, or if any of the input is 1, then the output will be 1. For the NOT means, if a single input equals to 0, means it's the output will be 1. There are also another two elements in the logic. One is the NAND, the other one is NOR. So NAND means, so basically it's to put a NOT on the AND, right? For the AND, right, both inputs have to be 1. Well, for the NAND, it'll be different, right? Just the opposite part of the AND. And for the NOR, it's the same. Put a NOT on the OR. Now let's look at the AND OR gate. So for an AND gate, so a gate means it's a logic, right? It's a logic. You can think of it as a gate that controls the current, right? If the AND gate means for example, in figure A, both switches have to be closed. Means both switches have to let the current go through in order to have the light to be turned on, right? So this is the AND gate. Well, for the OR gate, you can see as long as one pass has current, for x1 or x2, well, there will be current goes through Y, and the light will be on. So this is the OR gate. Either the current can go through x1, or it can go through x2, or it can go through both, right? So this is the OR gate. And so Boolean algebra and a truth table is a table that shows that use 0 and 1s to show the logic, right? For example, for the x1, we have all the possible values of 0 to 1. And how many combinations of the input? The combination will be 4, because we have two inputs, right? x1 and x2. x1 have two values 0, 1, and x2 have two values 0, 1. So the combination will be 4. And for each of the combinations, then we can calculate what is the output value. For example, when x1 is 0 and x2 is 0, so it means what? It means the output will be 0. Because, think of it as, remember that, the light switch, this is x1, and then you get x2, and this is the light bulb, right? So only when both x1 and x2 are closed, the light bulb will be turned on. Because right now it's all open, so which means it's 0, light is not on. So only combination is this one, right? When both is on, it's on. So this is how you use a truth table to understand the logic, and in what occasions that the value the output will be activated. So first of all, you need to list all the combinations. Well, for the OR, it's the same. So we can list all the combinations of x1 and x2 values, 0, 0, 0, 1, 1, 0, and also 1, 1. Then you can find out, okay, in the combination of 0, 0, what happens? It's OR, so it's 0. And but for 0, 1 or 1, 0, because there is at least one input has a one value, so which means that the output will be 1. When both are 1, of course, it also be 1, right? So this is more like this is the OR. Okay, this is the label. This is the label. All right, and a not means, all right, so when we have one value, so for example 0 to 1, the not will be they are the opposite value of the input. So when the input is 0, so the output will be 1. When the input will be 1, and the output will be 0. So this is the not truth table. So if we look at NAND and NOR, it's the same. First, we list all the combinations of x1 is 2. You can see it here. And then we look at AND, right? So if it is AND, what happens here? And if it is AND, then we'll have 0 here, right? 0 for this combination, 0 for this combination, and 1 for this combination. Well, the NAND means we are putting a not on the AND. So basically, we choose the opposite value of the AND. So that'd be 1, 1, 1, 0. So this is how you can use the truth table to understand the logic of those input variables or parameters. Same with NOR. You just need to find what is the OR here. OR, this will be 0, be 1, 1, 1. And then if you put a not on top of the OR, you just get the opposite values for the all OR column. So it'll be 1, 0, 0, 0. So this is how you can use truth table to demonstrate or describe the NOR logic. All right, now let's look at some of the symbols for logic gates. So there are two systems. One is US system. The other one is the ISO system. Both systems have been used a lot. So in the US, a lot of times you might see this version, but also you can see a lot of graphs actually have this version, and that's why it's important to understand both, to see both. And so for the US symbols, this is the AND symbol, and this is the OR symbol. And for the not, so there's a little circle at the top of a triangle. And for the NAND, it's the same. You just put a little circle at the end of the symbol. So this is the NAND and NOR. How it works. Well, for the ISO symbol, usually people just use a box instead of the other shape, and we put a symbol inside the box. So this is the AND, right? So then OR will be using this, and NOT we use 1, and this is the NAND, and this is the NOR. So this is the two symbol systems. Make sure you're familiar with both ones. All right, now let's look at when we know the logic control. How do we actually control the devices in the system? Then we'll have to use ladder logic diagrams, because this is a language that we tell the microcomputer, we usually call it PLC, processors, that how we want the system to do, right? So this is the language. Ladder logic diagram is the language that we tell the machines or tell the system about the instructions. All right, so the ladder logic is actually composed of the three main elements. One is the contacts. So contacts mainly are the input variables for logic. So the input can be switches, can be relay, or on and off sensors, or any other kind of devices, or some timers, any kind of devices, right? While the loads are actions, right? Load, for example, a motor running, spinning, that is action. A light is on, that is action. And a timer start to count, and it's also an action. So those kind of devices or contacts can be both the contact and also be the load for another logic. For example, a timer. We can use a switch to control the timer, right? In this case, the timer will be the load in the ladder logic, right? Well, we can also use that timer to control another device or another action, right? For example, alarm or motor or something. Well, in that case, the timer will be the contact, which means that is the input variable. So just let you know that those devices can actually serve as both contact and load in the ladder logic. So it's like your action can be triggered by someone else's action. Well, your action can also affect another person's action, right? So this is how it works. Well, another one is the power. So we have the power to supply the current. So this is a typical setup of ladder logic diagram. The reason we call it ladder is because you can see there are different different rows of a program, right? And each row we also kind of call it a rung, right? Rung 1, rung 2, rung 3, rung 4, 5, and more. And the two ends, they are actually connected to the power, right? You can see this two ends can all connect to a power. One is positive, the other is negative. Well, at the end, so usually the loads will be on the right, right? And on the load, sometimes we see the load will be the symbol of the circle. Well, in some other programs, you might see the load will be two parentheses like this, right? So just make sure you know that in different programs or different softwares, the symbol can be a little bit different. All right, so these are the sensors or switches, those kind of contacts. Well, this is open. This one will be the normally closed. So this one is normally open, one is normally closed. So what does it mean by normally open and normally closed? So normally open means the device remains off until it is activated, and then turn on the current. So which means there's no current when no current at the device when it is normally open. So for example, at this switch. This is a normally open switch, which means there's no current to go through this. Well, if for a normally closed switch will be this will be the normally closed switch, right? So at its normal state, it's always closed. Only when something is triggered, something is activated, it will turn to be open like this, right? To be open like this. Then there's no current. So if it is normally open or normally closed, you can just use the current to describe it, to think about it. And the letter symbol, you can see this is usually this is the input or the open contacts. And this is the normally closed contact. This is the output loads. Again, sometimes it might show like this. And this is the timer. This is the counter. Okay. So these are some of the common symbols we see in ladder logic diagrams. All right, now let's look at 4 examples. We're gonna use those examples to do some exercise and see how we can use ladder logic to do some programming for controlling. All right, the first one, let's start from very simple. To create a ladder logic diagram for the three basic gates, right? Three basic gates, AND, OR, and NOT. All right. So these are the three gates we have, right? So the AND is this symbol, and the OR is this symbol, and then the NOT is a triangle symbol with a circle at the end. All right, how do we do this? First, let's look at A. Will be the AND symbol. We draw this. This is the rails, from power, and the load. So load for the AND will be the Y, right? So we use the Y, the load, and then we have two input variables, or two contacts here, and because this is the AND function, or is the AND logic, so we put it on the same row. So this is the AND function. So this is how we draw the AND logic in the ladder diagram. Well, the same thing for the OR. Well, same, we have the load Y, but this time we use OR, so we're gonna use this as the input contacts. Make sure you understand that you can see all of those, in the first two rounds, in the first two diagrams, are X1 and X2 are normally open. So which means what? Which means they are more like this kind of switch, right? Normally open. There's no current at all. When it will have current, when this switch is activated and then closed, right? When it's closed, right? So this is how, for example, in the AND logic. So the Y will only be actuated when X1 has current, as X2 has current, right? When both two switches are closed. So this is the normally open. Well, on the other hand, normally closed will be what? Yeah, at a normal state, this switch is always closed like this. Right? It's always closed, right? So we can assume when this is normally closed, what happens? There's current, right? Just current goes through it, which means Y, Y is always running, right? Y is always running. When a Y will stop running, Y will stop running when there's activation on the X1, this X1 to change its value, which means A turn open, right? When it turn open, there's no current goes through, and Y will stop running, right? The load will stop running. So normally closed, that's why normally closed is usually used in some stop functions, right? Normally closed is often used in some stop functions. All right, so this is how we can use those simple ladder logic diagrams to show these three basic gates, AND, OR, and NOT. Now let's look at put a little bit of complexity in it. Look at another example, which is a push button switch. So push button switch is a very simple and common function we see in our lives, right? For example, a machine has a push button, and a lot of other things have a push button. Even the doors have the push button, and that how it works in a PLC system. Now we can let's read through the statement. So a push button switch used for starting and stopping electric motors and other powered devices is a common hardware component in industrial control system. As shown in figure, it consists of a box with two buttons, right? Two buttons, start and stop. One's for start and the other one's for stop. When a start button is depressed momentarily, by a human operator. So what does it mean by momentarily? So momentarily means the button will go back to its normal state after that pushing moment. So just push one time and then it will go back to its normal state, release it, right? So this is the momentarily means. Then power is applied and maintained to the motor until the stop button is pressed momentarily. And then when we want to stop it, we're gonna press the stop button, and then it brings power to the power to motor, and then so the power to motor is this, right? Then the power to motor is the output of the push button switch, but it also serves as a contact to the power to the motor, right? So this is what it means. So motor is only controlled by the contact of power to motor, right? And this power to motor function is controlled by the stop and start functions, right? So this is the basic understanding about this function, and we can let S1 represent start button, and then S2 represent stop button, and P to represent the power to motor, and then the M to represent the motor. So this is how these are the symbols we use in the ladder logic diagram. All right, now let's look at how can we write the ladder logic. So first thing is we need to understand about those what values it will take for each of the gate. All right. See what's happening at a normal state. At a normal state means we have not pushed our start button yet. We just let it machine stay by itself while the motor is not on, of course. So this is what happens. For this gate, right? For this gate, because it is the end, right? Because this is the end, so currently there's no current, right? Right now there's no current in this loop, right? There's no current in this loop. No current. But there is current in this loop. Why? Because this is normally closed. Normally closed, right? It's normally closed. This is normal state because there is for this path there is current. For this path there's no current, and also because it is the end. It's the end logic or AND gate, so there's no current here, right? No current here. Now let's look at what happens if we push the start button. Okay, so the moment we push the start button, and something happens, and there is current, right? There is current here. Now maybe I'll just use a different color to show it. Let's use green. All right. When we start to push the start button, the current will start to show, and because this is the OR, right? This is OR gate. So which means that as long as there is one branch or the one input is has current, or the value is 1, it will take the value of 1. So which means there is current here, right? There is current here. And in this case, what happens? And we come to another gate. So this is the AND gate. For the AND gate, in order for the output has current, or the value to be 1, we will need current or to be 1 at both branches, right? Both input variables. We have this because we hit the start button, and also we need to have this branch, right, to have current too. So this is also why this part has to be closed, right? Normally closed. Think about if it is normally open, what's happening? If it is normally open, means there is no current in this branch, right? There's no current in this branch, unless what? Unless you hit the stop button, right? Unless hit stop button. So now, if you do that, what happens is, in order to have the power to motor to run on, and you will have to push the two buttons at the same time, right? If it is normally, if this part is normally open. So that's why, we let this part be normally closed when there is always a little bit current here, and then we will once we hit the start button, we can make sure both branches, both inputs are taking the one value or have the current. That's it, we can have current. So this is what happens, at the moment of the start button is pushed. All right, we know that pushing of the start button is just the moment thing, right? It's the momentarily thing, and immediately it will be released. So which means this current will be gone. Now let's look at what happens after this start button is released. So which means the motor is running, right? So when the motor is running and and this start button is released, there's no current here, right? No current here. But we still need to maintain, right? We still need to maintain current to serve to the motor, right? To serve the motor. So which means we still need to make sure this gate always have the value of 1. How do we do that? Right? So now this is the value of this branch, right? The value of this branch is we reconnect this branch back to the OR gate, because right now it's taking the value of 0, and as long as one branch or one input has the value of 1, then we're good. So now if we have current, we are taking the 1 here, and then we'll take a 1. So this is how we keep circulating the current, right? And always make sure that this gate have the value of 1 or has current. Right? So this is the value of this loop. And the motor, of course, is only triggered or controlled by the power to motor. All right, so this is when the motor is running. Another option and action is we hit the stop button. Let's look at what happens to hit the stop button. So when we hit the stop button at that moment, right? So there will be no current here. Right? See, this current is gone. Right? This current is gone, which means this input will take a value of 0. Well, at the hitting moment, when there is still a little bit of current, at this side, so which means it's this can be 1. But because it is the end, right? Because it is the end, 0, 1 will return a value, or will come out with the value of 0. So which means there's no current, after at the other side of the gate, right? So in this case, if there's no current, then the motor will stop running, right? Stops spinning. So this is how you can use the stop button and our start button to control the motor. And all right, now let's look at back to normal state like this. Now let's look at how can we draw the ladder logic diagram. Now first we need to make sure that we know what values are taken, right? So define those variables. Start will be 0, normally open contact, as we explained just now. Start so when this contact is taking value of the 1, means it the switch is closed, and the stop button is pressed, right? Well, for the stop button, it's opposite, right? Because it's normally closed contact, right? It always has current, when at its normal state. So normally closed contact, which means normally it will take the value of 1. And, when we hit the stop button, and we'll take the value of 0. Well, for the power to motor and the motor, it's always when we hit the when we have the two because it's and when we have two input values both taking a 1, it will be 1, right? So power motor, the value of the 1 when both contacts are closed. When it will be taking the value of 0 when the contacts are open, right? All right, and for the motor, it's a motor will take 0 when it's off, and the motor will take the value of 1 when it's on. So this is now let's look at the truth table, right? Truth table will help us to understand the logic, understand the values. Well, first we need to come up with all the combinations of those scenarios. So one scenario is we have line 1 when the start is taking value of 0 and stop is taking 1, and line 2 is both are taking 1, and line 3 both are taking 0, and line 4 when start taking 1 and stop taking 0. So we because the power to motor is the end, so it only takes the value of 1 when both values, both stop and the start, are taking the value of 1s, right? Same, the motor, motor's function is the same as the power to motor, because it's the only one. Power to motor is only contact to motor. All right, after we have the truth table, we come to the ladder logic. How do we come up with the ladder logic? First, let's start from very simple. We know that P controls M, right? So the power to motor controls the motor. As long as P is taking the value of 1, M will be 1. So nothing else, right? So now let's just draw those symbols there. P controls M, and P will be the input variable in all the contact, and M will be the the load. So this is how we draw it. Now we get this function, right? And P is normally open. And then next, let's look at S1 and S2. So we know that S1 and S2 controls P, and it's analogic. Both sides should have current for P to run, so we can put the AND logic there. So this is the AND logic. S1 we know we have already explained that S1 is normally open and S2 is normally closed, right? So when S1 is turned on, right, or it's or is closed, so there's current goes through S1, and this because S2 is already closed, so P will be running, right? The motor will be running. So this is the AND function. But S1 with current or is closed is just one very short moment action. And its current, we know that its current will disappear after the push, after that pushing moment. So the question becomes, how can we use the logic to maintain the current, in this side of P, right? How can we use a ladder logic to maintain the current in this side of P, to make sure that after the start button is released, it's still the motor is still running. So we see that here is a OR logic, and there's another branch to come through this, right? So which means that we can add this OR function, right? Add this OR function to the S1 contact. add this OR to the S1 contact. Of course, P is normally open in this case. Right? And this comes to the push button logic, ladder logic. Push button ladder logic. We can go through the story again. So what happens is, all right, at its normal state, right? At its normal state, nothing happens because S1 it is normally open, right? P is also normally open, and okay, when we push the button, right? When we push the button, what happens? S1 will be closed, and there's current goes through this. Current goes through this, and P will be triggered. Right? P will be closed because P is normally open. P will be closed. P will be closed. Right? We come to the logic. P will be closed, and then motor will start to run. Right? Motor will start to run. So this is what happens. When we push the button. All right. Now, okay. After we push the button, when we release. Right? When we release that, what happens is, okay, when we release S1 button, because we have current going through this, right? This loop. So which means that as long as P is already triggered, there is current goes through this, this loop. Goes through this loop. Means P is closed, right? And then P is closed, right? So this path is always valid, right? So this path is always valid. Right now the computer is actually processing this path, right? Going through this path, not going through this path anymore because S1 is goes back already, went back to open. Now it's running this path, and P is closed, and then M is running. So this is how it works, after you release the start button, right? All right. So what happens after we, push the, when we push the stop button? So when we push the stop button, we know S2 will be changed to open, right? Change to open. So which means current will not go through this path, right? Current will not go through this path, which means that P will be go back to open, right? P will go back to open, and this will go back to open again, and M will be shut down, and the motor will not be running. So basically this is a story, how what happens when you push the button and then release the button and then stop it. And so basically the ladder logic control diagram tells this story. All right. Now you should understand why this S2 is taking. Why this S2 is normally closed, why S1, P, and M is not normally open, right? So this is ladder logic for a push button switch. So pay attention to this because this is a very fundamental function for turn on something, or control a very basic function. All right, now let's look at another example. It's a control relay. So a control relay can be used to control on and off actuation of a power device at some remote location. It can be used to define alternative decisions in logic control. Now construct the ladder logic diagram of a control relay. So for those who kind of forget what is a relay, just to give you a little bit background, and then let's go back to the, I think, 2 lectures before this lecture. And so a relay is a device that is actually triggered by the electrical mechanism because when the switch is closed, there's its current, right? And when there's a current, what happens is it will create a magnetic field, right? It will trigger the contact to this direction and then close this, right? When it closes, what happens is there will be a current, right? There will be a current. Will be current going through it. Right? And then becomes this, energized state. So there is a switch here to turn on and turn off the relay. Or another word, we say it, energized or not energized. And there is a spring system here, because once we turn it off, what happens is this magnetic field is gone, right? If this magnetic field is gone, means this switch, right, will be open again, right? When it opens again, there won't be any current going through this this path, and then it will become the not energized state. So this is a control relay, how it works. All right, now the question asks us to construct the ladder logic diagram of control relay. So which means that the relay can actually take on two values, right? Take on two values. When it's not energized, it's taking one value. When it is energized, it's taking another value, and that will be the alternative decisions, right, in the logic. So when the relay is taking a value of 0, it has one decision. When the relay is taking the value of 1, maybe they have another decision. Okay. And also the relay is controlled by a switch, right, or power. So we can call decision 1 will be the Y1, and we can call decision 2 with the Y2, since it doesn't really mention which one is what, right? So we can just say Y1 is when the relay is on, and Y2 will be the when the relay is closed or is off, right? All right, now let's look at this the diagram we construct here. So for decision Y1, right? For decision Y1, means the when the relay is is triggered, right? It's on. So which means its normal state, it will be the open. So means there's no current. When it will be on? When there is current, right? So when it is on, it will be closed, and then this run or this logic will start to run. So the whole system will have decision Y1. So this is what happens. All right. So when the relay is normally closed, what happens? So when the relay is normally closed, it means Y2 is always current here, right? And when what? When the Y2 is when the C is triggered, right? When it's not closed or turned back to the open, so what it means? When it turns back to the open means we get another decision, right? We get another decision, so it'll be Y2. So basically, this is how a relay actually controls the different functions from two different alternative functions or decisions. And of course, we have X to normally open the power to trigger the relay on and off, right? When it's on, what is it? When it's off, what is it? Right? So this is control relay. All right. After we talk about the exam 3, now let's look at another example. So the fluid storage tank example, it has a little bit more complexity in it, and so consider, now let's just read through the function and see what happens. So consider the fluid tank storage tank illustrated in the figure. When the start button X1 is pressed, right, momentarily, this closes the control relay C1, which energizes this solenoid S1 and opens a valve. So there's the valve here, right, and allow the fluid to flow into the tank, right? So when the tank becomes full, right? So when once they start to flow in more of the fluid or the water or fluid, any kind of fluid, so the fluid will go up, right? Will rise, the surface will rise, and then when the tank becomes full, the flow switch, that's a flow switch, is Fs, right? It closes, which opens relay C1. So opens relay C1, right? And provide a feedback to the relay. Open relay C1 and causing the solenoid S1 to be de-energized. So we will turn off the inflow. So which means F4, Fs will be the more of sensor, right? So switch. So to sense which level is the fluid right now. When the fluid is full, so it will tell the relay, okay, now it's time to shut off, right? All right. Let's keep going. Switch Fs also activates, right? Also activates timer T1, which provides a 120 delay for a certain chemical reaction to occur in the tank, right? So when Fs is triggered, what happens is it will start to count 120 seconds, right? During the 120 seconds, what happens? There is a chemical reaction, right? There's chemical reaction in the tank. So the T1 actually triggers that. And at the end of the delay time, the timer energizes a second relay, C2. There's another relay, the C2, right, which controls two devices. C2 controls two devices. One is the valve, the other one is T2, right? You can see from diagram. So it initiates timer T2, which waits 90 seconds to allow the content of the tank to be drained. So during those 90 seconds, what's happening is the fluid will go out, right? Will go out and drain from the valve. It also energizes the S2, which opens the valve to allow the fluid to go out. So which means when this timer counts 120 seconds, and the relay will let the valve open and also start to count 90 seconds, right? During those 90 seconds, it's actually the fluid will run out. At the end of 90 seconds, the timer breaks the current, right? At the end of 90 seconds, the timer breaks the current and then de-energizes the solenoid S2. And also close the outflow valve, right? So depressing the start button, X1 resets all the timers and open their respective contacts. So which means it's more the power, right? And construct the ladder logic diagram for the system. All right, so basically this is the whole system we're looking at. Now the question is asked us to compose the ladder logic diagram. So how do we do this? Well, step one is always, especially when we see such a lot of sentences of very complex diagram, is do not panic, right? Do not panic because of what? Because all complicated problems are composed of very simple problems. Okay? Yes, we see a lot of functions, a lot of sensors, switches, timers, counters in it. But all these complex functions are composed of very simple functions in it, right? Now let's just look at what are those simple problems here. Let's start from the very first part, which is the left part. Now let's read again. So when the start button X1 is pressed momentarily, this closes the control relay C1. Right? When this is the pressed start button and they close C1, causing the solenoid S1 to be de-energized, and it will turn off the energizes the S1, and then it opens a valve, allowing the fluid to flow, right? And when the tank is full, the flow switch, goes up, and then, going to a certain level, it will close, right? It will close, which opens the relay, C1, and then causing the solenoid S1 to be de-energized, turn off the inflow. See this function. What is this function? It's basically the turn on and off, right? Does it sound familiar with something? It's probably similar to the one we just talk about, which is the start and the stop button function, right? So see, what is a start? What is a stop? So the start will be this button, and stop will be this button, right? So Fs is more like a stop button, and it controls this C1. So this will P, this will be the motor. Isn't it the same? Isn't the same, right? So this is the same function that we just discussed before. Now we can just come to compose this very simple function. Very first function, and I assume you should be familiar with this ladder logic diagram already, because it's the same as a push button start and stop push button function, right? The start will be the X1, and the stop will be the Fs, and C1 will be the relay, and we use C1. This is the feedback. And also C1 controls S1, right? So this is a push button. One thing you want to pay attention to is Fs here is normally closed, right? It's normally closed, because if Fs is normally open, there won't be current going through, right? So that's why Fs has to be closed, normally closed. Well, other X1 and C1 are normally open. So when it only has current once it is triggered, right? All right, now let's keep going. So the second part will be this part. So the switch Fs also activates timer T1, which provides 120-second delay for a certain chemical reaction, right, to occur in the tank. So basically, this is the one action, right? This will be the one action. So switch controls a timer is one action. Well, at the end of delay time, the timer energizes a second relay. This is another action, right? This is one action, this is another action. So at the end of the delay time, the timer energizes a second relay. Now let's put that into our diagram. Put that to logics. All right, we use Fs, right? Fs and also T1. Okay. And also we have T2, which is a relay. So pay attention here. Fs is normally what? Is normally open here. So why FS is normally open here? Because for T1, for this action, right? For this action, the normal state is there's no current, right? There's no current. There's no current going through it. If there's when there's current going through the FS, at T1 will start to count, right? T1 will start to count, right? So that's why we need to put this FS here, FS as a normally open. And then for C2, same. So T1 will be normally open, and C2 will be once T1 is triggered, then after 120 seconds, T2 will be energized. Right, T2 will be energized. All right, now we have already went through a lot of those. Now we only have one last part of the function, which is this function, right? Now let's read through the last part. So C2 controls two devices. It initiates timer T2, right? Which waits 90 seconds to allow the content of the tank to be drained. And it energizes solenoid S2, which opens the valve to allow the fluid to flow out of the tank. Then at the end of the 90 seconds, the timer, it breaks the current and also de-energizes solenoid S2, and then close the outflow valve. Right, so it's from the sentence we can actually tell it closes the valve, right? It actually allows the tank to be drained, so which is more like open. It's another start and stop function, right? It's basically another start and stop function. If we have start and stop function, now let's look at which one is start device. So start device, because they control the valve, will be the relay, right? This is the start. And what controls the stop? It's a timer. The timer actually controls the stop. So timer will be stop function, and the relay will be the start function. Because we know how to write a start and stop function in a ladder logic diagram, so we just need to put that in our diagram. And this is how we compose the entire ladder logic diagram for the whole fluid storage tank problem, right? You can see all of those complex system looks like it's a really complex system, but in fact it's all composed of very simple actions, very simple problems. And after we compose this, we know now we understand how it functions. Right, so PLC is a very common control that we see in manufacturing, and it has been universally used in production systems. And knowing how to program PLC is very basic skill for engineers. So even for the managers, you have to understand how the controls are actually works in automation and production, and there are also several different vendors for the PLC devices, Siemens, and also some other brands, also popular used in both in the U.S. and also all over the world, and there are also some of the certification programs that you can once you know how to do the logic programming, and then you can go through all these tests, all these exercises, trainings that will give you a certificate. And when you're looking for jobs, and those certificates are usually very useful because they know that this is the part of the good skills for automation. All right, so if you want to master this skill for the ladder logic diagrams or programming, definitely will need a lot of exercise. And sometimes people can come up with very nice and neat logic to control a whole complicated system. I'm not saying that when we come up with a solution with the best solution to control it, but there sometimes maybe there can be multiple solutions to it, right? Some logic maybe can use very simple logic to control a complex problem. And all right, so that's all for today.